All right, welcome to another live Wells Tech training event. We are so happy you are here. Today, we are going to be talking about coils right here, and we're going to get into it probably much further than you ever have before. I got Rob Nordstrom here. He is our ignition system engineering manager. And if there's anybody who knows how a coil works, he's the guy. And he's going to be here today. And with us also today is Eric Obrata from South Main Auto in New York. And he had just put out a video where he had some questions coming in that he was having trouble answering. So that's why we're here. We're going to answer those questions with Rob. All right? But first, before we get started, we have to talk about, yes, the t-shirt giveaway. Yes, would you like one of these Wells Tech t-shirts? Of course you would. Here's the question. This is a secondary sine wave. Right? It's where the voltage drops down and the voltage spikes up right before the coil fires. What is this area of the sine wave called? That's your question. Okay? Text that in. First one with the correct answer will be sent a t-shirt. Okay, there you go. All right, without further delay, let's bring in Rob. Robert's way too formal. Rob Nordstrom. Rob has been with Wells how long?
About 4 or 5 years.
4 or 5 years. And he is our ignition system engineering manager.
Correct.
Right? Okay,
Correct.
So anything to do with coils, you're the manager.
Yes.
All right. And I asked Rob to come in because Eric Obrata had some questions that I couldn't answer myself.
Okay.
And so I needed an expert to come in. You're that guy.
All right.
How you like that?
I like being an expert.
And you know
every
what?
now and then.
Do you like to have fun?
Yeah.
Okay, we're going to have a lot of fun with this.
All right. Sounds
okay?
good.
Let's go. Let's bring in Eric. Where is Eric? There he is. Hey, Eric. Good morning.
Hello.
Eric.
Morning.
Mr. Obrata. Okay, Eric, I have got Rob Nordstrom with me. I hope you can see him okay. And you had some questions from one of the recent videos that you had put out on coils, right? Could you, and here's your opportunity. Here's your opportunity. If you can explain it to Rob, I'm sure he can answer your questions.
Sure. Well, if you guys know, we're on a YouTube channel there, and we had the Dodge Dakota in that had a misfire, a fish bite misfire there, and you guys can check that out on our channel. And when we were doing that, we captured some waveforms, known good waveforms of the ignition coil current ramp and the secondary voltage on the coil. And we also caught it during a misfire event. And there was some questions concerning, the coil and how it's wired internally. We had a lot of viewers that were asking questions and questioning us on our explanation of how we portrayed the secondary coil windings to be wired to the primary. And there were some questions about mutual induction and why we could see that secondary misfire reflected in the primary current ramp. So I think that would be something really good to talk about.
Yeah, I agree. That's very interesting stuff. Plus, if we can learn what's going on in the secondary through the primary side, hey, that is a great diagnostic tool to keep in our hip pocket here.
Yeah, I think that's really valuable, and not so much in the case of this Dakota where the coils are easy to get to, but what if we were working on a V6 and we couldn't see the back 3 cylinders, and all we could get to is current rate or primary voltage.
Right.
How can primary voltage help us, determining a problem with the secondary side?
Exactly. And Rob says it will. We can do that.
Absolutely.
All right.
Absolutely.
Okay, what I'm going to do you understand what's going on here?
I do.
Maybe what we should do is take a look at the wave patterns first before we get into it. Would you like to do that?
Absolutely.
Okay, can you bring up the good wave pattern first, Mike? Okay. And you can see on the top what we have there is the amp ramp. So at that point, we're looking at the amperage coming through the feed wire to that coil.
Correct.
Okay. And on the bottom side, what he has there is the secondary voltage as that coil fired. And everything looks pretty darn normal there.
Everything there looks normal.
You're right. Let's go to the next one. Okay, now this is that same coil. Is that not correct, Eric?
That's true.
Okay,
Yep, that's
and this is when it actually fired. And so you can see in here that we now have a ripple on the amperage side. So we're definitely looking at the primary side of that coil, but we got that ripple going on there.
Correct.
Which is very interesting. And I think that's mainly where Eric's question is coming in, and mine too. It's very interesting how that happened. And if you can take us through the steps to explain that,
I can.
that'd be great. Okay, let's take that down. And do you need the whiteboard?
Yeah, I'm going to use the whiteboard. And what I'm going to do is real quickly, looking at it from a mathematical standpoint, I think will help to...
I agree.
Will help to maybe answer some questions on exactly what's going on.
All yours.
Thanks, Mark. What's going on inside the coil from a more of a mathematical standpoint. Okay. I don't want to get heavy into any math or calculus or anything, differential equations or anything you do in engineering.
Yeah, don't
school.
do that.
Because it's
too far.
Yeah.
We just want to fix the car.
Exactly. So if you understand, though, I think maybe a little bit of where that mutual inductance or how this thing is actually functioning from maybe more of a theoretical standpoint.
Yes.
It might give you some insight.
Absolutely. What you did, when you explained that to me, it made absolute sense.
So there's an old formula for an ideal transformer, because essentially an ignition coil is just a transformer.
Yes.
But it's typically not being used the way a transformer is designed to be used. It's used to create a high voltage.
Yes.
So if we look at just the equation for how voltage is generated, it's Faraday's law, and you probably heard it. For voltage is equal to the number of turns times the change. I'm going to write change as a delta. We use that very common. That's magnetic flux, and this is delta magnetic or change in time. So this we're going to call flux, which is magnetic flux. Okay, so that's your magnetic field. This T here is time. The N is the number of turns of the amount of turns around the steel. So we're going to call this turns. And this is voltage. Okay. So looking at a basic transformer, what I'm going to do is just draw a transformer with an air gap like this. I'm going to put two coils inside here. So essentially what I'm doing is just drawing a basic coil. And this is all steel. We won't get into any of the design properties or anything, but this is the basic construction of a ignition coil. There's a primary and a secondary coil. So obviously these coils are wound, and this is in an XY plane, just a stack of laminations.
And that's a very generic design there.
Exactly. So what we're doing is when we are turning on the voltage to the primary coil, we are generating inside of this steel this magnetic flux.
Right.
It turns this into a north pole and this to a south pole, and in between here is a magnetic field. And inside this steel is a magnetic field. So what you need to understand to create any voltage is you have to have...
Let me step in just one second, because your drawing is a little bit confusing. This here would be the laminations that he's talking about.
Yes, this is
right
the
there.
steel.
Okay.
Yep. And this here right here is like, you've probably seen an air gap. But in a basic transformer, you don't even really need that. But
right.
It's just a place to store the magnetic field.
That's why you have that gap in between.
Correct.
And the lambs.
So this flux... So to generate voltage, you have to have changing flux in a changing time. So you have some sort of a changing magnetic field.
Something is happening through a certain period of time.
Exactly. So we change flux over time. That's how voltage is generated. This is just a multiplier. This links that voltage. So if I have 1,000 turns or 100 turns, it dictates how much voltage is generated. So,
and that's how you can go from like a 12 volt input to a 40,000 volt
exactly.
output.
So what we're going to do is we're going to just look at how the ideal transformer equation comes about from, this is Faraday's law. So because the change in flux over time is the same in the steel for the secondary and the primary, they're linked together.
Right.
So when I can rewrite this formula simply by solving it for the secondary coil and the primary coil together. So this is like a
show them how you break that down.
This is a little bit of
that was interesting.
A little bit of magic here. It's nothing crazy, but it's just a little bit of basic algebra. So I'm going to subnote the primary with a P is equal to NP. That's the number of turns. Change in flux over change in time. Right?
Correct.
I'm going to write that same equation for the secondary, and I'm going to subnote that with an S. Number of turns on the secondary.
Are you digging this yet, Eric?
Can you follow this?
Yeah.
It's not too bad for a Monday morning.
It gets better. It gets better.
Okay.
It all comes together here at the end.
Because this term and this term are exactly the same, I can move this N down here and solve it for this equation and substitute it back into here. So with a little bit of magic, we say that Vs over Ns is equal to this. I write the differential, sorry. This delta just means a change in something. So we have flux at time 1, flux at time 2. It's a change. That's all delta means. So now I can take this equation here, because I've solved it for this, and because it's the same for these two, I'm going to plug this into here, and I'm going to get VP equals NP times Vs over Ns. Okay? You see how I did that?
Mm-hmm.
So essentially,
yeah, he did.
I took this term here because it's this and put it in there. Okay?
Yep. No,
So
I got it.
It's real basic. So what I want to do now is I want to get the turns ratio the same. So with a little bit more magic here, I can take this Vs term and make Vp over Vs is equal to Np over Ns. Oops.
Right.
And this is your ideal transformer equation, and that's how they're linked together. So I can say that the voltage rise is equal to the turns ratio. And that's how the mutual inductance works. It's based on the changing magnetic field.
Right.
And because they're both in the same magnetic field, the same thing happens to them. The only difference is the change in the turns. So when somebody says it has a 100-to-1 turns ratio, it means that if I put 12 volts in here, I get 100 times that voltage on the secondary. Make sense?
Oh yeah, absolutely.
Okay, so this is just the number of turns in the primary to the secondary.
Right.
However, for an ignition coil, how that falls apart is you need to get the flux out of that steel really fast.
And that at the time.
Because if this number is really small, the change in time, and this number is really big, the voltage is really high.
Right. Time is crucial.
The time is crucial. So, this all being said, we know that we need to change the time in an ignition coil very fast. And that's why when you see that current ramp,
Right.
okay, that's just the charge of the magnetic field in an inductor.
When you charge that, you're charging that lamination too, right? Are you not?
Oh, exactly. Because if I just had a coil, let's just say this was a coil of wire, and I hooked this up to a battery, okay, and I closed the switch, the magnetic field is still there. It's in the air.
Right.
And it can't change instantaneously, a magnetic field.
Right.
The current can't go through those coils.
When it's building up, it builds up to a point where it comes to a consistent.
It's just saturated.
It's consistent then at that point. It's always.
Exactly.
Okay.
Because that field, once we reach a steady state voltage, you're not changing the magnetic field anymore.
Right. It's just flowing.
Yeah. So essentially what we have here is a magnetic field. When we put steel in there, because steel, you can have a magnetic field inside of steel, you can store it there. Now what ends up happening is you can use the properties of the steel to drive down the current when you collapse the magnetic field.
The swiftness of the drop
Exactly.
is determined by the steel.
Exactly. And the configuration of the steel.
Cool.
And the circuit. But we're not going to get into the circuit drivers.
No, it's kind of.
We just want to understand what's going on in this ignition coil.
Right. So what it comes down to then, what you're saying here is the primary and the secondary windings are related to each other through the lamination, right?
Yep. Due to magnetic coupling.
Right, through magnetic coupling. So if they're related to each other, what Eric saw was absolutely normal.
Absolutely.
Right, on his scope.
Yep.
Because he was getting a reflection of what was happening in the secondary through the primary side because of this.
And the way I like to think of this, for people that maybe get a little bit nervous around electricity and they can't see it,
Sure.
a transformer is a mechanical gearbox. It's an electrical gearbox.
Okay, that's a
Think
cool
of it
way to
that
think
way.
of it. Yeah,
The output and the input are related to each other.
right. Yep.
Okay, the horsepower in is equal to the horsepower out.
Depending upon what gear you got.
It's just all the speed ratio,
Right.
and that's all you're doing with this. Think of the amount of teeth on a gear
Yep.
determines the speed.
Yep.
The amount of turns in a coil determines
I've
the
never
voltage.
thought of it that way, but that's a great way to get a mental image.
If you're a mechanical guy and you think about gears and speeds,
Yep. That'll
this
help.
is just an electrical analogy
That's really
of a
good stuff.
mechanical gearbox.
So now let's bring up that second wave pattern one more time here, if we can. Now, if you look at that, you look at that amp ramp on the top, and typically that should just shut off. It should be pretty clean in that area right there. Now, what happened? What caused us to be able to see that ringing in this pattern?
Well, what's happening is typically when that. So I'm gonna. Is it okay to erase this now that
please.
everybody's
Here
had their
Here you go.
their fun math lesson for Monday?
No, that's wonderful.
But, it all comes from somewhere, these formulas, and they're really neat to understand that the equations show you
Right. Oh,
what's
yeah.
going on
It's all an
in
equation.
the hardware. So that's how we use that to design stuff. But so if we have an ignition, so I'm going to draw a standard, oops,
You run out there or something?
I think our black pen is getting, there we go.
There's a blue one there if you want.
So this is a typical current ramp, okay?
And that's what we're used to seeing. I mean, that's very typical.
Yeah, so this is your charge slope, and this is would be your dwell time. So your ignition module is going to give, this will be 12 volts. I'm just going to put this as time.
Okay.
This is time, and this is voltage on this axis, and then current would be black. So we'll just say I is the black one, okay?
I means voltage to these guys, by the way.
I is current.
Oh, current, I mean.
V, yeah,
Yes.
I is current. So the current waveform going into the coil, so this sharp transient is what gives you that voltage spike.
Right.
So when you're looking, so this is, we're going to call this the primary side. And then the secondary side, we're going to put it down here under the same type of event, kind of like in your
Wave pattern.
wave pattern.
Mm-hmm.
So what actually happens is when you see this voltage like this and it goes like this,
Mm-hmm.
if you notice, it's exactly that same duration.
Right.
And it's
It
at
is.
minus 1200 volts usually, ish, in there, because this is at 12 volts, right?
Mm-hmm.
This is at negative 1200 volts, based on the way that the windings
How many
are.
turns you have. Right.
So that initial bump down here, and then you see the spike, and then the burn, and then the ringing going down, right? So that's
Right.
your typical output of the secondary.
Yep.
Well, this 1200 volts is generated just by turning on the primary.
Mm-hmm.
And that's the mutual inductance that he was talking about.
Right.
That's the change in flux, happens on the primary side, happens on the secondary side. The turns ratio is what gives it.
Right.
How to get this spike, though, is to clamp that voltage, or clamp the current here.
Right.
It causes that increased spike.
Right. That downward spike occurs at the same time that is going downward.
Exactly. And this is
that the current's been shut off.
exactly. So this peak kV is what flashes over the spark plug, and then this is what essentially burns, right? So this
That's
is
the burn
this
time
is the
for
current
it.
flow
Right.
through
the spark.
spark plug to ground. So if you don't have any way for that current, for that, for everything to drop down,
Right.
eventually the magnetic field disappears. So there's no stored voltage.
Right. It isn't like a capacitor.
Exactly. Once that magnetic field has disappeared, there is no more voltage.
And it's designed to do that.
Exactly.
Right.
Yeah, that's inherent in the design. So what he's seeing in his secondary waveform that's shadowed up here is the fact that it never does go into a burn situation in the engine. Is
Right.
essentially, it looks like this.
Or it was very, very short.
And
right.
then it goes like this, because all of this is happening, either it's arcing to the engine block, the head,
Right.
wherever it's attached to, it's not going into the cylinder.
Right. It's not lighting up a spark plug.
Exactly.
Right.
So what ends up happening is this is mirrored back through the magnetic field onto the primary side of the coil.
Right. And so you are going to get that ring like he
Exactly.
got.
Because if you have
Just because-
voltage,
Right.
you have current.
It's dissipating.
And that's why it shows up on that current waveform.
Yeah, it's dissipating current is what you're seeing.
Back onto the primary.
Whether it's firing a spark plug or not, you're going to see a dissipation of current, especially if it's slow. If you really, really, really look close at a normal firing event here, you may see a little ring here.
You might see some smaller rings.
Right, but normally that's not where we look. But when you didn't fire, like you were saying, either it fired inside the coil or fired outside, we can't tell. It looks like it fired inside the coil, but you will get a ring like that because of that.
Because think of the secondary wire or the winding as a long piece of wire.
Yes.
And it's wrapped around.
And that's all it is one piece of wire.
So there's a voltage drop of about 20 kV along this long length of wire.
Yep.
Now, because they're wrapped around each other,
Yep.
there's a voltage differential between there that could get into a couple hundred volts.
Yeah, absolutely. Yes.
And it'll just arc to itself. It'll short back to itself. So there's a lot going on in here.
Yep. I think there is. And you know what? We're running short on time.
Okay.
And Rob, I don't know about you, Eric, but I'd like to have him back over here. And I don't care if you like him or not. I like him. So I'm going to have him back, all right?
Yeah, I'd have him back.
All right, and maybe what we can do is get more into this and a little bit deeper so we can really understand what's happening with those scope patterns.
Yeah, absolutely. I mean,
we'd appreciate that.
yeah, absolutely. And what I'd like to share with you is how we actually test an ignition coil.
Let's
on
do
our
that.
bench.
Let's do that. And then you can actually see. Maybe what we can do is we can actually have the broadcast from there.
Go into our lab.
Go into the lab That would be fun.
Because there's an SAE specification for engineering.
Hey, Eric, when you come up here to visit, let's do that. Let's go in the lab with Rob here and blow some stuff up. That's the best part of this job.
Yeah. Because we'll fire these ignition coils right into a capacitor.
Yeah. You should see what these guys do in a lab. It's a lot of fun.
Yeah.
I in my next life, I want to be a lab guy. All right. But for right now, we got Mike over at the car. So we're going to scoot over. We're going to shoot over to Mike right now, and he's going to show us how to do it right on the vehicle.
Sounds good.
All right?
All right.
Thanks, Rob. We'll see you.
All right. Thanks, Mark. So here we have our 97 F250. This has a 5.4 liter in here, and came in with a P0304. So we went ahead, and first step, as always, we went out onto Identifix, checked out what causes misfires on this truck, and most commonly ignition coils. So pertains perfectly to what we're going over today. We went ahead and found out there was an ignition coil, and actually looking at Eric's video a couple weeks ago, he brought up a good term. He called it caveman diagnostics. Well, that's what we did first. We went ahead and swapped the coils, and our misfire followed our coil. So we know that we have a bad coil. But this truck was really easy to change the coil out on. There's vehicles that aren't. V6s where the coil's under the intake or something like that. This is where a test with the amp clamp on the primary ignition side can really save you some time. So went out to all data, printed out our wiring diagram, found our primary power wire is a common wire fed between all the coils. So I hooked an amp clamp here onto both of our primary wires. One amp clamp on the bad one on the good one. You can see that here. And I'm going to go ahead and just turn these amp clamps on. And go ahead, they're on the 1 millivolt, 10 milliamp settings. Going to zero them both right away. And these are pretty easy coils in terms of the way they work. Just like we were talking about, like Rob was talking about. They have a single power wire in, and then they're ground side controlled by the PCM. These aren't module style coils or anything like that. So you can test them just like Eric had been talking about where he hooked up on the amp clamp. So we're going to do that now.
And I learned something today too, that you can actually amp clamp it on either side. I
Right,
always thought it was the feed side.
On this style coil, yep.
And don't confuse that now. When you get a coil that has a module on, you need to go to the feed side.
Right.
But a two-wire coil,
Yep.
you can amp clamp either side.
All right, so we'll start with the good coil. I'm going to go ahead, hook it up to our scope. And why don't we go ahead and fire the truck up and see what this thing does. And I have a trigger set up on the scope, and I'll show you guys how to do that, just to help capture the image. All right, I'm ready.
Ready? Clear?
All right. And hopefully, there we go. We can see our current ramp just like Rob had drawn out on the board. We got our current ramping up, and then the PCM shutting it off, and it dropping down immediately. So this is a good diagram of a coil.
That's a great diagram of a good coil.
Right, and this is our trigger piece right here. So wherever we move this trigger, it's going to pick up the voltage in there. If we move it up here, we're not going to see anything at all. We got to move it down where the voltage is reading.
That's a good point.
And that's through the setup, through trigger, and then you select trace 1 and turn on auto trigger. And wherever you move this thing now, it'll read.
Right. So you want it low enough where it's going to pick up a voltage.
Right. Yep.
Or
Okay, so
we're looking at amps, but it's actually voltage.
I'm going to go ahead and swap over to the other.
Yeah, let's take a look at
the other coil now. Now this is our bad coil. And hopefully we pick something up here. There we go.
There it is. Why don't you freeze it right there?
All right.
Okay, I'm going to shut the vehicle off.
Okay. Sounds good. And you can see our current ramps up just like the other one did, and then drops off when the PCM shuts it off. But like Rob was talking about, there's nowhere for that energy to go. It's not crossing the spark plug, so it's actually oscillating inside of the ignition coil. It's arcing internally.
Yep, that's what that means. It's arcing internally.
Right.
And I misspoke a little bit before when I said that scope pattern meant that it was a good coil. It doesn't mean that it's necessarily good. It means that it's not arcing internally.
Right,
is
right.
what it
Yep.
means.
Okay. Yeah, this is for sure a bad coil.
Mm-hmm.
It's arcing internally. There's the spark's not getting out across the spark plug. So we do have it arcing internally. That's enough information right there to tell me to replace the coil.
And honestly, I just learned that because, you know, I haven't seen that pattern before,
Mm-hmm.
and before Eric had brought it up.
Yep.
But look at this. What a great way to check coils, especially two-wire coils
Yeah.
like this. And like you said, when you have one that's buried behind the manifold, you can get that, you
Right.
can get to it. Plus, in past broadcasts, we showed you how you can go through the fuse.
Right, yeah.
So now you can go through the fuse and look that way
And
too.
you'd see them all at once.
Right,
then.
you can see them all at the same time and pick it out that way. And then you'll need a trigger to tell you which one is one,
So you
that
know-
type of thing. Right,
yeah.
a trigger signal. That's a little different setup, but you can go back into our videos and see
Right.
how to set that
So
up.
this here is a good picture of an internally failed coil. Now commonly on these 5.4s, on this engine, the coil will actually, the boot will fail and it'll actually fire out through the boot,
Right.
through the engine block.
Yes,
That will actually look okay on here.
right.
It'll, because the spark is going somewhere.
Right.
It's got a path to escape.
It doesn't know, the scope doesn't know if it's firing internal or externally.
Right.
It's not
So-
going to, you know, define the difference between that.
Right, so
Right.
don't get fooled by that.
Right. But if you got one, like you pull up mode 6, especially on a Ford like this, pull up mode 6, and all of a sudden you get a few misfires here, like number 6, few misfires, few misfires.
Right.
So is that an injector or is that a coil? What's going on here?
Right.
A great check. Get that amp clamp on there
Yep.
and see if it's internally
Yeah,
arcing.
I didn't have to take anything apart. All I did was
Yep.
hook the amp clamp over the wire, hook it up, and
Right.
we're
You're
ready to go.
Good stuff. Great stuff. I guess we got a lot of comments here.
Yeah, let's see what
Holy
we
mackerel.
got.
All right. Let me first talk about the sine wave that we were talking about at the beginning. The correct answer for that is spark time or burn time. Spark line, any one of those answers is correct. So can you bring up my email there? There. If you've answered that question correctly, send me an email with your mailing address and your shirt size, and we'll get a shirt out for you. One of these really cool Wells Tech t-shirts right there. Yeah, these are really cool. All right. And that's about it. Do we have any other questions in here? Insulated by
Actually, he was asking about using the paddle, and we did show the paddle.
the
in a different
Oh
video.
yes, okay, the fly swatter.
Yeah.
And
yeah.
and that, you know, the problem with that is you would see that it was actually firing with this because it's internally arcing, and that would confuse you because
Right.
if you're just using the paddle on this, you're going to get a fire line.
Right. Yeah, it'll show it. It'll
Right.
Show it
So be
working.
careful with that. You know, if it's not firing at all, you might be able to see that with that paddle, and that's what we were showing the last time.
Right,
It was
yep.
a not fire at all. So keep this in your arsenal. And by the way, if you have a U scope, you can use that too. That works great for this.
Exactly,
You know,
yep.
so Eric was using the Virus or whatever he had there.
Yeah, I think
but it
he's
was a
got
snap-on
that.
scope, so
Yep.
we use that one too. But we could be using the U scope for this.
Yeah.
So there you go. All right. Anything else?
No, I think that's it.
This was great. Hey, if you like this kind of stuff, you know, where we bring out engineers and we talk about this kind of long hair stuff.
When we pull the guy out of the lab.
Yeah, and if you like it, let us know because we can do more of this kind of stuff. We got engineers all over the place. And yeah, so yeah, this is great stuff. And I love it. I love it, getting into it and really see how this stuff really works. I love it. But
Yeah.
if you guys love it, we'll do more. All right?
Sounds good.
Thank you for being there. Without you being there, we would not be here. And we'll see you again next time in the Wells Tech Garage.
See you then.
All right, let's go fishing.